Hey, there we go. All right. Hey, we're gonna do some AP chemistry practice. I think we this would be a good idea to do some of the basics of chemistry first. So let's get right into it. So the first question is, what is chemistry? What are we actually doing here? Okay. It turns out chemistry is most simply it's the study of matter. Okay, and it's like, okay, that's great. What's matter? Well, matter is, as this prompt says, here's stuff, right? It's what makes up the entire universe, air, glass, planets, whatever. It's anything that has mass and volume. Okay, so chemistry is the study of that. And not only that, but a better definition is the study of matter and the changes that it undergoes, right? So reactions and how these things interact together, stuff like that. All right. Okay, and then that leads us to question, well, what's a substance? Okay, well, it's something that has defined fixed composition. Okay, what that means is that no matter where you take it or how you look at it, it's always the same. For instance, an element iron, pure iron we're talking about. Doesn't matter if you split it up into little chunks, into different pieces, it's going to look the same, it's going to have the same properties. It's defined and it's fixed in its composition. Okay, same with water. Water is a substance. It's has a certain it's got a same look to it. Everywhere you do it, doesn't matter where it comes from, how you make it, it's the same thing. All right. States of matter. We there is plasma, you probably know about that, but the three main ones are solid, liquid, and gas. Solid is something that has a fixed shape and doesn't conform to the container. Okay, so for instance, look at this little sample here. Even if you let's say we put a bunch of like flour into a glass, well, it seems like it's going to as it says a liquid here, it has a varying shape and it conforms to the surface. The flour would seem to conform to the surface of the glass, right? But remember, you got individual little small things that look like a liquid, but it's still a solid. Okay, so it's just a fixed shape. You pour salt into a container, it looks like it's a liquid because it conforms to the shape of the container, but you still have individual little pieces. Okay, so that's what solids are. They just don't conform to their container. They have their own shape, and they're not defined by how hard they are. For instance, solid iron is rigid, but if you take a solid sodium metal, you can cut it with a knife. So, all right, what about a liquid? Well, it's something that has a varying shape, and that means it conforms to a container. Okay, so for instance, if you pour water into a square-shaped glass, it's going to look square. Okay, if you pour it into this beaker here, it's going to look like the shape of the beaker. But notice it has an upper surface, so it doesn't take up the entire beaker. Okay, what about a gas? It's something that conforms to the container, but it has no surface because it fills the entire container. Let's look at the molecular level. So these particles here, and it's all, look how organized they are. Look at the packing. It's like the packing of vegetables at like Sprouts. Let's look at a liquid. Notice that we still have a little bit of organization, but they're pretty moving around each other, disorganized. And what about a gas? Well, a gas, the particles are really moving around. They're far apart, not very close together, and they're very disorganized. All right. Properties of matter. Well, now that we're chemists, we're interested in what are the characteristics that identify these things? What about them can tell us that we're looking at a certain material? That's the question. So for instance, there's two things we can talk about, the physical part of that and then the chemical. What is a physical change or a physical property? A physical property is something that we can talk about without it actually turning into another substance. It's just what we can identify just by the actual substance itself. For instance, color, melting point, electrical conductivity, all things that don't actually change anything about the substance. It stays the same. Okay. So for instance, let's say we talk about a physical change where we alter the physical properties, but not the substance itself. Water can go from a solid state ice and it can melt into water, but it's still water. So physical change is the same thing before and after. All right. Um, let's talk about a chemical change. Well, a chemical property is something it shows up whenever we're talking about it interacting with something in a chemical way, meaning that it changes into another substance. For instance, it's things that are flammable, right? You light a paper on fire, it's gonna be something else. It's not gonna be paper again, right? Corrosiveness, like for instance, rust on a car. When metal rusts on the car, it's no longer that same metal. It's very different, right? It has different properties. It's brittle. What about reactivity? Well, with acids or some other chemicals, specific ways that they react or change into other things. So let's say we have water. If you pass a pretty strong electrical current through it, it changes into two different substances, hydrogen and oxygen. They have different properties. They are not the same thing as water. That's a chemical change. Sometimes they give you, imagine there's a microscope so powerful you can see the individual atoms, and they give you little windows into the atomic world, and you have to be able to tell if there's a chemical or physical change sometimes. Let's look at the first one. Is this a chemical or physical change? Well, let's look at the atoms before and after. So I see a bunch of some of these red balls, right? And the red ones are bonded with the blue ones, the particles. Let's look at the after. Well, look at the difference. There's some red ones now. They're doubled up and the blue ones are by themselves. So it's a different arrangement of these particles. It is a chemical change. What about this one, chemical or physical? Well, we have these red balls, but notice even though they're split afterwards, they're still their same red balls. So this can be like representing particles of water. They're together, but if they're apart, they're not different. They're the same red ball, physical change. Here's some examples of real metals or in other things. How about copper? Copper is a physical property because you can easily hammer it into a sheet. That's not going to change into another chemical. It can also have a certain density, right? So any sample will have the same density. Any sample, big or small, will have the same melting point, boiling point, etc. What about some chemical properties? Well, this is things that changes copper into something else, maybe another form of copper. This copper can actually change in moist air into this certain chemical. It can react, and we know it's reacting because we see bubbles, we see heat or light, and maybe even another solution. It changes, that solution will change the color, right? And when you remember, color is a physical property. If you change it into another color, there's a good chance that it's a chemical change now. All right. How about some temperature changes? Well, as you saw, for instance, you could take water, or excuse me, ice and heat it up and it becomes liquid water. And then you could heat it up again, it becomes water vapor, right? So the main point here is that a physical change can be caused by heating and it can generally be reversed. Not the same thing for a chemical change. If you burn a piece of paper, you're not really going to be able to put it back together now, will you? So notice that physical changes can usually be reversed. Chemical cannot. Okay. So here they give you some examples here. So how about this one? Purple iodine vapor appears when solid iodine is warmed. Well, look, it's still iodine at the end. Is there a change or not? There's not a change. Solid iodine turns into another form of the same thing, iodine, physical change. Gasoline fumes are ignited by a spark in an automobile's engine cylinder. Ignited, well, that sounds like fire, flammability. That's a chemical thing. It's going to turn into a different product. A scab forms over an open cut. Well, this one seems a little confusing, but remember, as long as you see some different change, right? So the scab looks different from the rest of the other skin, huh? So it's probably a chemical change occurring. All right. So what's the central theme in chemistry? It's just understanding, well, ultimately we're big humans and we see these changes, but we don't see them on the molecular scale. So the whole point is we need to make tests so we can do that. We need to be able to measure chemicals in the lab and react them in certain ways to study chemistry. Okay. And so another form of that is energy. Energy is really something, it's the ability to do work. What that means is that it's to do something. So you eat chemical energy, sugar, that allows you to move around and do something, and your cells are doing something. Different types of energy. Potential is about position, right? So a weight raised above the ground has potential energy because that means it can do something, it can fall. All right, stuff like that. Okay, we're going to skip the model stuff here. Units of measurement. Okay, so the way we actually do chemistry is we have to measure things, measure changes. How do we do that? Well, we need a system to measure things. And the one system we use in all of science really is the metric system, so called the SI units. And we have different physical quantities. For instance, mass, how much of something there is. We use kilograms. That's not weight, by the way. Weight is a measure of gravity. Length, for instance, how long something is. Usually we use the meter. Feet and other things like that are just too ambiguous, too confusing. Time, well, seconds is the smallest unit, and that's the unit we use for different things. How about temperature? It's actually not Celsius, as you see, it's Kelvin. You probably know about Kelvin. And how about this one, amount of substance? Well, you would think like grams or weight. It's actually the mole. We'll talk about the mole too. All right, let's talk about the SI units. Notice that it's very systematic way. It's always the same and it's very useful. Let's talk about for instance, the ones that are above factor of 1. Okay, well, let's talk about kilo, for instance. That's pretty famous. So what do these mean, really? It's a prefix that is multiplying by a certain factor. Okay, so for instance, kilo means a factor of 1,000. So let's say we're talking about a kilogram or a kilogram. Well, gram is the base unit, and we're saying that we have a factor of 1,000 of those grams. So 1 kilogram literally means 1,000 grams. How about mega? Well, it's got a big M and it means 10 to the 6th. That means 1 megagram is 10 to the 6th grams. How does that work on the other side of the scale when we're talking about below zero, smaller amounts, really small things? Well, centi is a pretty popular one. But here's what it means. The factor it multiplies is actually less than, or sorry, it's not less than 0, but it's a fraction of a number. So centi literally means 100th, right? I'm using the th there, 100th of something, meaning a fraction of something. So centi literally means multiplication factor of 10 to the negative 2. So 1 centimeter literally means 10 to the negative 2 meters. It's 100th of a meter. Okay. Now, no, there's technically what you can reverse it a little bit. So, what if we don't want to say 10 to the negative third seconds is 1 millisecond? You could also reverse it and say, well, let's make 10 to the negative third a positive exponent and say 10 to the third. So you can reverse it and say, well, what about milliseconds? What if I want to put that into a multiplication factor? You can do that. You can say 10 to the third, or 1,000 milliseconds, is 1 second. So just note that the bigger, excuse me, the if you say like a second, well, that corresponds to, you can represent it as a bunch of smaller fractions of a second. So if you use bigger things, they should always be represented with smaller amounts. That's a key. Alrighty. So we can do an example here. So what if I said, well, oh, sorry. Okay. I could say, what if we said, well, we have 1 milliliter. Okay. How can we represent that? Right. Well, you can represent it in terms of liters, right? Milliliter just means, remember, that's the prefix, milli. Okay. And so we're saying, well, what does milli mean? Well, milli literally means 10 to the negative third. You can look at the chart. And then we still have the same base unit. So as you see, 1 milliliter is literally 10 to the negative 3 liters. Another way to represent that is, well, you can flip them, right? So what if you said, well, 10 to the third milliliters, or really 1,000 milliliters, is 1 liter? You could do that. All right. So here's some examples. Now notice you can cube units too. In fact, volume is usually cubic meters. That's the derived unit. Just some information to get from that. We can actually relate milliliters and centimeters cubed. It turns out, for measurements, 1 centimeter cubed is exactly 1 milliliter. That's very helpful for conversions. All right. So for instance, if you saw something that said the density of water is about 1 is about 1 gram per centimeter cubed. Okay, that's another way of saying exactly 1 gram per milliliter, because you can interchange centimeters cubed and milliliters. Okay. Temperature is simply the measure of how hot or cold something is relative to another. So that's usually in Kelvin or Celsius or Fahrenheit. But when we say temperature, it's not the same thing as heat. Heat is a measure of energy, like the ability to do something, right? The atoms are moving around. The atoms have the energy moving around. And so if something is really hot, we say, or it has a lot of heat energy is what we really mean. Okay. And it's all about how it flows to a lower temperature. Okay. For instance, if I took a hot chunk of metal and I put it next to a cold chunk of metal, okay, cold does not travel. Cold is simply the absence of heat. Only heat travels. So the heat is going to travel from that hot brick into the colder brick till it equals. Okay. Now, you should know how to convert Kelvin and Celsius. Here's the formula. To convert from Kelvin to Celsius, you can say, or either one of these. The point is, to get to Kelvin, you take your Celsius and you add 273.15. To get to Celsius, you can take Kelvin and subtract 273.15. Pretty simple. And this is showing simply how they're related to each other. Notice Celsius and Kelvin are an absolute scale. So notice 0 is the absolute bottom of Celsius, 273 is the absolute bottom of Kelvin. And so 100-degree change in Celsius is really the same change in Kelvin. Notice that because they're absolute units. Notice because of 32 not being 0 for Fahrenheit, the change in the boiling point is not going to be the same. Notice it's not a 100-degree change. It is something else because it's not 0. All right. You should also be able to, of course, convert temperature and Celsius. Those equations are fairly simple. Uncertainty. Let's talk about sig figs. The whole point of sig figs, it seems really confusing. Sig figs are simply a way to make sure that we're not overestimating our data. Okay, so for example, let's say I measure something and I have a certain amount of precision to it, right? It's something I know for sure. Well, imagine I do some math and my actual answer, let's say I use too many decimals, my answer is more precise than the numbers I started with. That doesn't really make sense. Your precision is limited to your least precise measurement. It doesn't make sense to make up precision. You don't know much more information about your least precise unit. So that's what we use sig figs for. So here's how you do sig figs. There are a different couple rules. In general, it's pretty simple. Here's the rules. First of all non-zero digits are significant. So look, 5, 1, 2, 1, 9, 3, 8, they're all significant because they're not, just by virtue of not being 0. Simple. What about all zeros between non-zero digits? Well, they are significant because they're in between two significant numbers. So notice the 0 in front of 5, the 0 sandwiched between 5 and 2 is significant. The 0 sandwiched between the other numbers is significant too. All right, and then here's where it gets not difficult, but just the two main other things. Notice that leading zeros that occur before the first non-zero digit are not significant, okay? The reason why is, well, look, all these zeros here are just representing, it's kind of like a placeholder just for the other digits. So all those zeros before really don't mean anything. The only thing that matters afterwards is the numbers in front of that. So notice after the 0.00, we have 502. Now 5 and 2 are significant because they're anything above 0, and 0 is between them, so it's going to be significant too. By the way, you can convert these numbers to scientific notation always, and it'll make it really simple to find how many sig figs you have. So for instance, let's say we have 0.5316, okay? Well, first of all, this 0 is not significant because it's in front. It doesn't represent an actual, it's just a placeholder for the other numbers. Doesn't have any meaning. Okay, but let's say we wanted to find the significant figures or digits. Well, all of these are non-zero, so they're significant. So this has 4 sig figs, this one, this one, this one, and this one. But what if I wanted a really easy way to do that? You can convert this to scientific notation. Now, by the way, what is scientific notation? It's simply a way of expressing really small or really big numbers into a power of 10. Let's say we have 5, 3, 0, 0, 0, 0, 0, 0. That's annoying to write down on paper. How do we actually represent that? Well, we have a 0 in this placeholder, right? Excuse me, we have a decimal that is separating the tenths and the hundredths, the right side from the whole numbers to the left. So we can actually represent this in terms of a whole exponent of 10. I'm going to move this decimal so that I have one number in front of it. So I'm going to go 1, 2, 3, 4, 5, 6, and 7. So it's going to be 5.3, 0, 0, 0, 0, 0, 0. and then it's going to be times some power of 10. And it's some power of 10 because that's what that is represented every time we skip over. That is a multiple of 10. That's why it's times 10 like that. What's the exponent? Well, remember, as we go left to a number, it gets bigger. So it's a positive one in this case because we move to the left, it's positive. And how many times did we move over? Remember, we went 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th. Now you're probably like, well, you're still writing a lot of zeros here. Yes, but many problems, you're not going to have that much significance. So usually it'll be rounded to, for instance, 5.3 and then times 10 to the 7th. So that's a way to clean up these numbers and represent them much easier. Now, how do we do the sig figs again? Well, again, we can simply move the decimal place. In this case, we're going to move it to the right. You have to have one whole number in front of it. So we're going to move it to the right once. And so it's going to be 5.316 times 10. But remember, as you move to the right, you get smaller number. So it's actually negative. So we move once, so 10 to the negative 1. That's how you do scientific notation. All right. And so, of course, make sure you do a lot of practice with sig figs, but that's how you do it. Okay. Now, what about for calculations? That's the most important part. So, for instance, multiplication and division are the simplest. You simply keep the fewest significant figures. Okay, here's what that means. Let's say we're doing a volume calculation. We're taking 9.2 centimeters that we measured, and we're multiplying it by 6.8 centimeters from another, maybe we're measuring this graphic composite. So we take our ruler, one side is 9.2 centimeters, one side 6.8, and the other side is 0.3744 centimeters. We want to get centimeters cubed, so we're going to multiply this. And we're going to multiply 9.2 centimeters times 6.8 centimeters times 0.3744 centimeters. Now notice your calculator is probably going to spew out a lot of decimals. Your calculator has nothing to do with actual significance in the real world. It's just a machine for calculating things. So this would not be a correct answer in real life. Because look, your significance is bigger than any significance you previously had. So we need to use the smallest number of sig figs. 9.2 is 2, 6.8 is 2, and 0.3744 is 4. And remember, we don't count this zero here in the front. So we're going to go with the smallest number, both are 2. So therefore, you're going to round 23.422464 to 23 because that's 2 sig figs. So basically, we cut off all this because it's not known, it's not significant. All right, and then don't forget you can use units algebraically. So you can multiply centimeters times centimeters times centimeters, that's centimeters cubed. What about if you're using addition and subtraction? Well, you're not really using sig figs, you're just simply using the fewest decimal places, okay? So let's take this example, 83.5 milliliters plus 23.28 milliliters. The question is, even though your calculator would spew out something like this, 106.78, or on your paper you would get that. The question is, well, what is the real answer based on known accuracy? Okay, well, you would add them up normally, and notice that the smallest number of decimal places is the 83.5. It only has 1. So therefore, your final answer must be rounded to 1 decimal place. So that's why we say 106.8, because the 7 here, the 8 right next to it bumps that up to an 8. Okay. All right. Rounding off is simple. Remember, that's if it's more than 5, you round up 1. If it's less than 5, round down. Most of you know that. Okay. Exact numbers. Sometimes we have no uncertainty associated with it. Those are unit conversions. Okay. So guess what? When we do 60 minutes in 1 hour, that is exactly 60 minutes for 1 hour. How many centimeters in 1 inch? 2.54. That is exactly known. There is no significance for those. So guess what? When you're doing calculations, you cannot base your final answer of significant figures off of those exact quantities. Okay. Let's do an example. Let's do 50. Hmm, there's the erase function. Oh my gosh. Okay, I hate whatever that is. Okay, we're gonna do 48.0 divided by 11.55 centimeters cubed, and then grams on top, okay? Well, the easiest part is what's the unit? Well, remember, you can treat the units algebraically, so it's simply grams per centimeters cubed. That's your unit, okay? And you're just gonna do the math. So 48 divided by 11.55. So I'm still used to Windows 10. All right, so 48 divided by 11.55. Okay, now look, the calculator spews out all these numbers, but significance, folks. How many sig figs is the least? Well, 11.55, those are all non-zero. That's four sig figs. And this one has three sig figs. Why does it have three? Well, even though there's a zero, notice that the zero is to the right. Remember all the zeros that are leading, so 0.001 or whatever, these are unsignificant. They're just placeholder. These have actual meaning after the letter. Okay, and so those are actually going to be counted. So 48.0 is actually three sig figs. And therefore, 3 will be our final answer. So our answer has to be rounded to 3. So it's going to be 4.16. 4.16 grams per centimeter cubed. That's how you do it. Okay. Let's time to understand unit conversions. Give me a second here. Okay. We are back. We're back. Okay. Sometimes you guys are going to have to do a lot of calculations involving converting, and that includes stoichiometry. So this is a big deal. So what we can actually do is we can take certain known units, we call them equivalent quantities, and we can multiply by them, and that could actually get us to where we need. Let's say, for instance, we know the fact that 12 inches equals 1 foot. That's certain, okay? No uncertainty associated with that. All right, doesn't matter if it's not metric, we still know that, okay? It's a fact. Well, what if we wanted to convert, let's say, 12.6 inches into feet, okay? Well, we can actually use this fact here to convert that, okay? Here's how we do it. Well, we can actually say, well, we know that, let's say we solved for one side, and so we divided both sides by 1 foot, okay? So here's what's interesting about this. 1 foot divided by 1 foot is 1. So guess what? This fact that 12 inches over 1 foot, it equals 1. So that means that if we multiply this conversion factor we derived by the inches, that would actually be multiplying by 1. And so we're not actually going to change the amount here. We're simply changing the unit that represents it. This won't actually work though, because you have to cancel units. But guess what? What's awesome about these conversion factors is you can flip them. So it's just as correct to say 1 foot isn't 12 inches the other way. No problem. So we're going to multiply by our 2.6 inches. Okay. And notice that, so we got our conversion factor, we're multiplying what we're trying to convert. And as long as your units cancel like that, because remember, we're basically dividing at this point. So inches are on the top of the fraction and inches are below, they're going to cancel. So we'll basically get 2.6 divided by 12. And our final unit will be in feet. Sig figs will be 2 because 2.6 was 2 sig figs. You don't get the sig figs from the 12 inches or 1 foot. That's exact quantity. All right, so that's how you do that. Okay, notice that There you can generally represent it as here's the beginning unit. Make sure the beginning unit is canceled on the bottom, and you always end up with your final on top. Sometimes it's on the bottom. That doesn't matter. Okay. Now, what about converting between unit systems? Well, it turns out that sometimes we need to convert between feet and meters or whatever. So let's say I wanted to convert 15 feet into one meter, or not 1 meter, sorry, 2 meters. How many meters is 15 feet? Well, sometimes you have to do multiple steps. Well, let's say we want to go from between feet and meters, but here's the problem. There's no direct conversion, but there is a direct relationship between, or sorry, let's say, no, we'll go with feet. We'll go with feet. That's fine. So let's say we want to go from feet to meters, but um, it would be better if we said, well, there's a middleman here because there's no direct conversion that exists between feet and meters, but there is a direct conversion between feet and centimeters, and then centimeters has centi in it, and that's related to meters. So we can say, what's the relationship between feet and centimeters? Uh, I think it's and usually they would probably give you a chart about this. Um, okay, no, I was thinking of something else. Hold on a second. Ah, I was thinking about miles and kilometers. That's it. Okay. So sometimes we're given, let's say we wanted to convert 15 miles to kilometers. I'm sorry, I was thinking of something else. Well, um, you can have direct conversions between different unit systems. So miles is American, kilometers is metric. Um, so it turns out there is a specific relationship that you could find on some table or some chart. It's known that 1.6093 kilometers is in 1 mile. So you take your original miles there and you can multiply by this conversion factor. Notice the miles are canceling out because one's on the top, one's on the bottom, and then you're left with that proper unit. Okay. All right. So, let's talk about some other types of conversion factors. Anything that is a derived unit, meaning it has two or more units, can be a conversion factor. For instance, density. You're used to converting density and mass in those problems that you do in like 8th grade because we have an equation and we can manipulate it around. You might have seen that little chart of the pyramid where density is in one and mass in volume or the other. You cover up one, and then it would show you how to divide or multiply. But this is how you really do it. So you can say mass is mass divided by volume is density, but let's say you wanted to convert to volume. Well, you can actually, depending on, you can be given the density, for instance. So let's say we do an example where we say 5.2 grams per 1 milliliter. Let's say that's the density of some substance. Well, you can actually multiply by the volume as an example. Let's say you know the volume is in this substance, this sample is 5 milliliters. Well, the units will cancel and then you'll get your grams. So you don't even have to take that formula, density equals mass times volume, and then rearrange the equation. You can actually just take the fact that density itself is a conversion factor right here. And as long as you multiply by the correct units that cancel, you're good to go. You don't even have to change anything. So definitely get used to that in chemistry. All right. And lastly, what's an extensive property and what's an intensive property? Extensive is dependent on the amount of substance present. Okay. So for instance, mass, right? Notice these bricks of copper, the smaller it is, the less it weighs. 8.9 grams. Bigger samples weigh bigger grams. So it depends on the amount of substance. But what are some things that don't depend on the amount of substance? It turns out things like density, right? Color, right? Notice the color's the same, the way it shines, And also, so density, you can actually calculate the density based on the volume of each one and the mass, and they're all the same. So density does not change based on how much you have. Okay. There's another example of an intensive property is melting point. If you have a huge sample of copper and a small sample, they're both going to melt at the same melting point, believe it or not. Okay. Alrighty, guys, that's about it. Make sure to do some practice problems. Good luck.